We're going to look now at the problem of a particle, like an electron, in a well of finite depth. To anticipate the answers, I'm showing here the typical results we'll get for this problem. Just like the infinitely deep potential well, we're going to get solutions for very specific energies. Though here, there will only be a finite number of them confined to the well. You can see 3 in this example here. We will also see a combination of the kinds of behaviors we've been looking at. Inside the well itself, we are seeing sinusoidal solutions. Though, because these walls have only a finite height, these sinusoidal solutions do not hit 0 at the walls, but rather they penetrate some distance into the walls. We can see that the higher energy solutions penetrate further into the walls, which is again what we would expect from our experience with the particles and barriers of finite height. We also see, as before, that each higher energy solution has one more 0 than the previous one. So now let's see how we derive all this behavior.
So let's look at our finite potential well. We're going to choose the height of the barrier here to be V0 on either side of our potential well. And we'll choose the origin for our energies. Down at the bottom here is 0 for our potential energies and all of our other energies. The thickness of the well will be Lz, as before. But now we're going to choose the position origin in the middle of the well. This will turn out to make our algebra much more convenient to write down. So we'll be going from minus Lz over 2 on the left to plus Lz over 2 on the right, and z is moving in this direction, of course. So if there is an eigenenergy E for which there's a solution to this problem, then we already know what form that solution has to take. It has to be sinusoidal or cosinusoidal in some way in the middle, because the energy is going to be above the bottom of this well. And it has to be exponentially decaying on either side. We'll throw away the exponentially growing solutions on both sides as being unphysical. The particle would not be anywhere in the middle if we did that, and we wouldn't be able to normalize the wave functions. So we keep just the decaying parts of the exponential on both sides. So for some eigenenergy E that we're hoping to figure out here, we know that if we knew what E was, then the k vector, or the k magnitude in the middle of the well, would be the square root of 2me over h bar squared, where m was the mass of our particle. And similarly for the exponential decay constant on either side, with our energy E below the top of the barrier, then we would have kappa equal to the square root of 2m v0 minus E all over h bar squared. So for z less than minus Lz over 2, that's over here, we would be saying the solution is a decaying exponential. Now, because we're heading off in negative directions, we've got a positive written exponent here, but this is going to decay as we move to larger negative z and some unknown coefficient g out front. And in the middle, between minus Lz over 2 here and Lz over 2, we're going to have some sort of sinusoidal or cosinusoidal solution. We've still got to figure that out, with 2 unknown coefficients, a in front of the sine part and b in front of the cosine part. And then for z greater than Lz over 2, we're going to have an exponentially decaying function on the right, f e to the minus kappa z. And of course, we still have to figure out all of these constants a, b, f, and g as we work through our solution. To move forward here, we're going to need to apply the boundary conditions to solve for the unknown coefficients in this problem. So those are the constants a, b, f, and g, and of course we hope to establish the eigenenergies E as well. And so, just to summarize, our solution on the left is going to look like this, our solution in the middle is going to look like this, and our solution on the right is going to look like this, with these constants we're trying to figure out. We only need to figure out 3 of them in our algebra, actually, because we could establish the 4th one by normalizing the entire wave function if we wanted to. So let's start looking at this problem, and we'll be looking at boundary conditions. First of all, we'll look at the boundary condition corresponding to continuity of the wave function. Now, incidentally, this algebra is going to take quite a few steps, and it will seem moderately complicated. Each of the steps is straightforward, but it does take a while to go through them all. And I would say this is about as complicated a problem as we want to tackle in this kind of analytic fashion. More complicated problems like this we would solve by numerical techniques probably, but we can manage this one analytically, and it will show us quite a lot of interesting things. So we're going to work through it, even though it will take us a little bit of time and a little bit of algebra. So here's our wave function at Lz over 2 just on the right-hand side of the barrier. It's going to start out like this. And just on the left-hand side of the barrier over here, we're going to have some combination of sine and cosine-like wave functions. To simplify our writing, instead of writing e to the minus kappa Lz over 2, we're going to write instead x sub L. And instead of writing sine k Lz over 2, we're going to write instead just s sub L. And instead of writing cos k Lz over 2, we're going to write just c sub L. So, writing this equation for continuity of the wave function, that this should equal this, in our shorthand notation that becomes fxl equals a sl plus b cl. So this is the exponential decaying part, this is the sinusoidal part, this is the cosinusoidal part at Lz over 2. Similarly, at z equal to minus Lz over 2, we would have gxl is minus asl plus bcl. And continuity of the derivative, the other boundary condition, will give us at z equal to minus Lz over 2, gxl multiplied by kappa would equal to k times acl plus bsl, or we can take that k down here. We get the kappa from differentiating the exponential, and we get the k from differentiating the sines and the cosines here. Remember, differentiating a sine gives us a cosine, differentiating a cosine gives us a sine with a minus sign in front of it, but the argument here is minus Lz over 2, so that minus sign combines with the minus sign corresponding to this and gives us a plus sign in here. And at z equal to Lz over 2, we're similarly going to get this relation from the continuity of the derivative. So we've got four relations, these two from the continuity of the wave function, and these two from the continuity of the derivative of the wave function. Now what we need to do is to find what solutions are compatible with these relations that we've derived from the boundary conditions. So we can add this equation to this equation. These are two of the equations we got from the continuity of the wave function at the boundary. And when I say adding two equations, I mean I'm going to add the left-hand side and see what that gives me, and I'm going to add the right-hand sides and see what that gives me. The sum of these left-hand sides must equal the sum of these right-hand sides. So that would give us 2bc sub L, but these two terms would cancel. So I'm going to bring those over to the left here. Adding these two up, I'm going to put them on the left. And then adding these two up will give us f plus g times xl. Similarly, subtracting one of the continuity of the derivative conditions we came up with from the other one, subtracting one of these from the other, subtracting this one from this one, these terms are going to cancel out, and we'll be left with 2bsl and kappa over k f plus g times xl. Now, as long as f is not equal to minus g, so anything other than the condition f equals minus g, then we can divide one of these equations by another one of these equations. If f was equal to minus g, this would be 0. and we can't divide by 0. It doesn't give us a definite answer. So if f is not equal to minus g, we can divide one of these by the other, which means we end up with sine over cosine, which is tangent. The other terms cancel, the two b's cancel on both sides, and we've got just the same thing here as we have here, so we're left with the kappa over k. So we get tangent KLZ over 2 is equal to kappa over k. And this is a relation that in the end will allow us to figure out what the eigenvalues are, the energy eigenvalues. Subtracting this equation from this equation, I'll get cancellation of these terms and I'll end up with 2ASL here. So here's 2ASL. And I subtracted this one from this one, so I've got f minus g times xl. Adding these two boundary condition relations, similarly, I'm going to cancel these two terms. I'm going to end up with 2 of those. So there's my 2ACL on the left, and adding these two gives me minus kappa over k f minus g times xl. So now, as long as f is not equal to g, we can divide this equation we just figured out by this equation we just figured out. Again, if f is equal to g, this would be 0, and we can't divide by 0. So as long as f is not equal to g, we can divide this equation by this equation. That gives us minus the cotangent of KLZ over 2 is equal to kappa over k. Cosine over sine gives us a cotangent. And we had a minus sign sitting here that we've taken over to the left-hand side. And this relation is also effectively a condition for eigenvalues. And we're going to work with this relation later on to figure out the energy eigenvalues also. So for any case other than f equals g, which leaves tangent of KLZ over 2 equal to kappa over k, but not this condition. We can't get that condition because we'd be dividing by 0 and we wouldn't get this. Or, so either this condition or this condition, f equals minus g, which would give us this condition applying but not this condition. For any case other than these two, we would appear to have both of these relations trying to apply, but that can't work because the tangent of this is never equal to the cotangent of this. And so these two would contradict one another. So the conclusion is that the only possibilities are that f is equal to g or that f is equal to minus g. So, first possibility, f is equal to g, and then this condition is going to apply. Or f is equal to minus g, and this condition is going to apply. So let's look at the condition f is equal to g, in which case we know that this condition is going to apply. Well, note from this equation that we had here, and this one that we had there, that if f is equal to g, this is 0 and this is 0, so the right-hand side of both of these equations are 0. But it's not possible for SL, the sine, and CL, the cosine, to be 0 at the same time. If the sine is 0, the cosine isn't 0, and if the cosine is 0, the sine isn't 0. So the only way that these equations can work is that if A is equal to 0. Hence, inside the well, A has to be equal to 0. That means the sine part disappears because it was A sine kz plus b cos kz, so we're only left with the cosine kind of wave in the middle of the well. And here's two cosine-like results that we might get. So this is cosinusoidal. Relative to the middle of the well, it's falling off on either side. Similarly with this one, this is also cosinusoidal. These would have different k values associated with them, and at the moment we're just guessing that these would turn out to be eigenenergies, but we'll prove that later on. Note that these functions are both even functions. That is, whatever value they have on the right of the centre, they have the same value on the symmetric point on the left of the centre. And that's true here as well. The other possibility would be that f is equal to minus g, in which case this condition would be holding. And again, if we note from these two equations, if f is equal to minus g, then this is 0 and this is 0. So the right-hand sides of both equations are 0. But we never have a condition where the cosine and the sine are both 0. It's not possible. So as before, now we conclude that b has to equal 0. Hence, inside the well, in this case, we have to have the sinusoidal solution. Remember, it was a sine kz plus b cos kz. Now the b has to be 0, so we're just left with the sinusoidal part in the middle here. And that is an example of a kind of result we could get there. Again, guessing for the moment that this is an eigenenergy. And we see this is an odd function. Everywhere on the right, if we look at the corresponding point on the left, we see the function on the left is minus what we had on the right. That's true both for the sinusoidal parts and the exponential parts. Now, though we found the nature of these possible solutions, we've not yet proved that these are actual solutions. We still have to figure out what the eigenenergies would be. So we've not yet formally solved for the eigenenergies E. And hence we've not yet formally deduced what K and kappa actually are, because we need to know E in order to figure those out. We're going to find E by solving these equations. Now, these equations don't solve in a simple analytic way, but we can still solve them. At least we could solve them numerically, and there's a nice graphical way of looking at the solutions of these equations. So let's solve for the eigenenergies. We're going to change to dimensionless units here. The energy unit we're going to use is this one. We'll take this as our unit of energy, which is, incidentally, the first level in an infinitely deep potential well. You may remember that formula here, but it's a convenient unit nonetheless, and it does have some physical meaning to it. So this is going to be our energy unit. So instead of talking about energies E for the moment, we're going to talk about energies epsilon, which are E divided by this energy unit. So this is actually a dimensionless quantity. And similarly, we can talk about a barrier height here, nu naught, that is actually, which is V naught divided by our energy unit. Also, in terms of these energy units, originally we had this formula for K. We can rewrite that in here using this quantity E1 infinity, just a little algebraic manipulation, putting this in, you can check that. And equivalently, that's pi over Lz times the square root of this dimensionless energy epsilon. And similarly for kappa, this was our original formula for kappa, we can check this substitution in here. We put in this energy inside the square root and check this all out. You'll find it's equal to that. Or equivalently, pi over Lz times the square root of nu naught minus epsilon. So, consequently, we have this equation for kappa over k written in the dimensionless units, nu naught minus epsilon over epsilon, square root of that. And for KLZ over 2, using these dimensionless units, we would have E over E1 infinity here in the square root with pi over 2 are on dimensionless units. That's pi over 2 times the square root of epsilon. And for kappa Lz over 2, again, similarly, we would write that as pi over 2, the square root of nu naught minus epsilon. So this tangent equation, tan k Lz over 2 equal to kappa over k, becomes tan of pi over 2 times the square root of epsilon equal to the square root of nu naught minus epsilon over epsilon. Or we will rewrite that for a reason will become apparent quite soon in the following form, taking the square root of epsilon over to the left-hand side and putting it in front of the tangent here, and leaving the square root of nu naught minus epsilon on the right. Similarly, for the cotangent condition, it will become similarly just the square root of nu naught minus epsilon over epsilon on the right and pi over 2 root epsilon inside the argument, or equivalently we can take that root epsilon over to the left here as well. So now let's look at how we're going to do a graphical solution of these equations. We're going to choose a specific well depth. We can do this calculation for any specific well depth. So suppose, for example, we chose a well depth of 2 units. And what we do here is we plot this curve, which is the right-hand side of these various equations. And that's what it would look like for 2 units of well depth. Or for 5 units of well depth, it would look like this. Again, you see it's this kind of square root curve. Or for 8 units of well depth, it would look like this. So we start our solution by choosing the well depth for our problem, and we graph up this curve on here as a result. Then we add the curves corresponding to the left-hand sides of the equation. So one of those curves is square root of epsilon times this tangent. So that gives us this function here. Actually, that heads up to infinity, and then it comes back from minus infinity and goes on like that. And the other one is the cotangent curve, again with the square root of epsilon in front of it, minus square root of epsilon times the cotangent. And that gives us these blue curves here. And again, this one headed up to infinity and came back from minus infinity. Now, for a specific nu naught, such as nu naught equals to 8 here, the solutions of our problem, the eigenenergies, are the values of epsilon at the intersections of this curve, the square root curve, and these 2 curves here. So explicitly, one of those solutions, one of these intersections, is for epsilon equal to 0.663. And we could get that off this graph if we'd used a very sharp pencil to do it. Of course, we can solve these on the computer as well by simultaneously solving this relation here with this one. And the second solution would be with the cotangent, and that would occur at 2.603 energy units. And the third solution would occur at 5.609 energy units. And you'll note there are no more solutions here. There are only these 3 intersections with this curve here and either the tangent or cotangent curves. So there are only 3 eigensolutions inside the well. So these are the actual solutions. Of course, I knew the answer before I started this, so what I was plotting you before were the actual solutions to the problem, but we'd not proved that at that point. This is the first solution here, this is the second one, and this is the third one. And there are only 3 such solutions in a well of this height, of this depth. Note that they are all, incidentally, at lower energies than the corresponding solutions we would get for an infinitely deep well of the same width. So this is 0.663 here, and if we look at the solutions that we would have got for an infinitely deep well of the same width, this would be where the first solution would be for that infinitely deep well. This is where the second solution would be, and this is where the third solution would be. And all of these are at lower energies. And the reason for that is that they are less curved. So in the original potential well with infinite depth, I had to fit an entire half period of a sinusoidal wave in here. You'll see I'm not fitting an entire half period of a correspondingly sinusoidal or cosinusoidal wave here. This wave is not as curved, and so it has less kinetic energy, and the same thing is true for the other ones.